taking this last-minute addition to the schedule. It was driven largely by the spectacular success of the New Horizons encounter with MU-69. It's certainly a message that is not new to me, but it's made manifest just how powerful the stellar occultations are and what they can do for us. And I want to make sure that we don't miss out on an opportunity for additional science and study of small bodies in the solar system simply because we didn't talk about it. So one of the point of this talk is to show you what it took to get these results, what we're getting in terms of mission support, and where the actual problem is that we need to address as a community. So we certainly are spending a lot of mission dollars on small bodies missions right now. I think it's an amazing time for small body research. I've just listed some of the ones that I can remember off the top of my head, a couple of them newly funded, and some that have just recently completed. But we're making great strides in progress in understanding these small bodies across the solar system, all the way in from near-Earth asteroids, all the way out to the Kuiper Belt now. And those of you that understand and work with small bodies know that while it's great to have individual examples, we also need to understand the populations as well and how they vary. But one of the things that has opened the door for us is an amazing mission from the European Space Agency called Gaia. When I first heard about this, I couldn't believe, first of all, that somebody actually built something like this, because it sounds like such an esoteric endeavor just to do a kinematic map of our galaxy, and which you guys probably didn't care about all that much. But what it does for us in measuring the positions and three-dimensional velocities and distances to these objects is you have to actually measure where the stars are to an incredible level of precision. And it's sort of the next step in the space-based astrometric catalogs that we've had. Typically, the positions that we get from the Gaia catalog are, it's now becoming my new favorite units, is the micro arcsecond. These stars are known now to 1 or 200 micro arcseconds, and they also give you proper motions. And also for spacecraft navigation, it's also really important to note that these are tied to the same fundamental ICRF, the inertial coordinate reference standards that are used for spacecraft navigation as well. In the past, we've had questions and problems between star catalogs that maybe we're not measuring, our ground-based measurements of objects are not in the same reference frame as what we're doing for our spacecraft navigation. So we have always had strong components of optical navigation for spacecraft to acquire the target and the encounters work. But Gaia is founded upon those same standards, and as we found from New Horizons, this actually really does work. But the thing that it's done for us now is that it has increased our ability to predict stellar occultations. And in fact, what was routine 20 years ago in the main belt asteroid population is now more or less routine in the Kuiper Belt. The difficulty scale is basically linear with the increasing heliocentric distance. And so up to now, we've been kind of stuck with working on the very largest Kuiper Belt objects because those are the ones that we can predict. And prior to the Gaia catalog release, a stellar occultation of an object like MU-69 simply would have been impossible. We would not have been able to do this. Now, one of the important point about Gaia is that it is measuring moving sources. The stars are all moving around in the sky. They are measuring the positions, they're measuring the motions, but as soon as Gaia completes its mission, which is somewhere between 2020 and 2022, though the knowledge of the positions of those stars will begin to erode with time. So 10 years later, we won't ever be as bad as we were before, but it's going to start to close out the small end of the size distribution, and it's going to close out the outer solar system gradually as that catalog degrades, until such time as maybe they can fly a second Gaia and extend the arc out, which I've heard that they're talking about doing. So I want to caution you to think that we have time to think about this. We don't. We're wasting opportunities right now, and I'm going to show you some of the things that we're not going to be able to do. So I want to give a quick summary. You've already seen a little bit of the results that Alan showed in the previous talk about ME69 occultations. We chased 4 events, 3 in 2017, 1 in 2018. This is a very new kind of deployment, a very large network of telescopes that are all mobile and a consolidated, working as a team all together under one umbrella. Normally, there are not that many occultations that have deployed that many stations at once, and it's usually by a bunch of people that are very, very loosely coordinated and trying to do their own thing. Not that they haven't done some really interesting stuff, but this is another notch up for doing these small objects. So, but the point here is that chasing these 4 events cost the project, and this is coming out of a mission budget for New Horizons, cost about $1.25 million, okay, to chase these 4 events. Now, that cost really doesn't include much of the cost of Sophia, since that's heavily subsidized. So that was an additional expense that was carried by the Sophia project. So this largely was the cost of doing the 3 ground deployments with the 24 stations. About 10% of that cost was the actual equipment, buying the telescopes and cameras and things like that. And we use those, and they have a lifetime that will extend out. And I made heavy use of volunteers. So that means I wasn't paying salaries for every single observer. I was trying to use locals as much as possible, as well as amateur astronomers and other people that I know in the United States that came out. So these things are very expensive. You imagine, I don't know how many of you have ever gotten $1.25 million from a standard RNA grant. I'm not sure that, I've never done it. You're talking about smaller amounts of money to do this. And the only way that we did this was because we were coming off of the mission budget. So now the value of these occultations, you heard Alan talk about this, I'll go really pretty fast. The number one goal was to get an albedo so that we knew how to set our exposure times. Fortunately, that turned out to be in a reasonable place, though part of the early strategies was trying to remove the large and dark chase. So if it had been, say, a 4% albedo, that would have really changed the sequencing. And so the very first experiment that we did, the very first occultation, was designed to eliminate that one particular case. At one point, I thought it did, but that's a long, complicated story. I don't have time to tell. But the secondary thing, which was really important, was targeting. And by this, I mean targeting the New Horizons spacecraft to the encounter. We had observations from the Hubble Space Telescope that were pretty good. Each individual measurement is good to about 10 to 15 milliards. So we're limited by the signal to noise of the Hubble data, not the catalogs. But the occultation measurements, when we do that, we actually can tell you where the object is relative to the star to better than a kilometer. That's 34 micro arc seconds. Okay, so we're actually limited by the Gaia catalog, even for the astrometric position that we infer from astrometry. You cannot, there is absolutely no way to get that level of measurement precision on this target with Hubble. And we also wanted to know whether or not it was one object or two objects. And we got our first occultation. There was a lot of different interpretations. Once I got the last occultation in Senegal in August last year, it was pretty clear to me that we were dealing with a contact finding. That's a great piece of information to have going into an encounter. But think about how we can use this going forward. If you want to go out and say, well, is MU69 an unusual object, or is it typical? Well, we could just use the typical theoretical thing and say, well, the one that we found at random can't be a special object. But sure would be nice to know. And in fact, on the mission, Alex Parker has done some statistical calculations on here that indicates that the objects that we were going to find with Hubble, we can make a case that we were going to find an object like MU69. That if it was a large amplitude, broadside light curve, we might not have recovered it because it would have been too faint when we went and recovered. We have one such object that we found that we tried to recover and didn't find, and maybe that's, we have a selection bias that is selecting us and forcing us to find and go, it's a cool object, but how representative is it? You need to do more of these occultations. Or you can send more missions, but I think the occultations turn out to be a lot cheaper. So here's a quick example of what we did after that first resolved image came down. And you can see them overlaid here. There's a lot of work yet to be done here, but it's certainly indicative of how well the occultation data matched what we saw with New Horizons. And in fact, where there are deviations, basically we're looking at topography. And to be able to be sensitive to topography on the object, not only that, but the nature of it being a compact boundary and what have you, is pretty incredible. In fact, I'm kind of hoping that this is going to improve our spin period and polar orientation for the object once these can link back to the occultation data from the spacecraft data. So moving on, as good as success as it was with New Horizons, I'm also on the Lucy mission. And I'm looking at ways, I already knew that this was helping out with New Horizons quite a bit. I want to take advantage of this tool and make the Lucy encounters better. And so I've already been starting to look, and here's an example of the whittled down list of occultation opportunities for Lucy targets prior to launch. It launches in October 2020. Okay, 2021, sorry. So these are color-coded by fiscal year. The two at the top, I'm going to show you the result of that occultation in just a second. We've actually succeeded with occultation of Lucas. But we have a few other objects to chase after. And the problem here is, even though it's a mission budget, this whole list here is going to, I've estimated, will cost me something like about $2.8 million, which isn't even, it's too high for even the Lucy mission budget. So we're going to have to pick and choose, and I think the ones that have an asterisk on the left are the ones that we are currently targeting for that, and even that is going to push $1 million chasing those. And so there's a bunch of other events, and we could actually do some interesting exploration of all these other targets if we had more resources to chase after these occultations, including Gaia, and that's actually just a main belt asteroid, but just to give you a sense for this. This is, I believe, it's a 10-kilometer-ish object, and I still think I can do this one with stellar occultations. In fact, I would say that I can get the probe down to about 5 kilometers with these techniques. Just a quick rundown on what we've done with Lucas. This is this weird one that has a very, very long rotation period, about 3 weeks. And based on a single successful cord from amateurs and working together with MIT, a single cord was able to tell me where to go in November this past year. And the one that I want to show you is the results from November 18. This is the occultation profile of Lucas. Now, from the light curve data, everything else we had other than occultations, you would say this is just some strange prolate ellipsoid, and it's not. It's not a simple triaxial ellipsoid at all. There's a huge amount of topography and strange behaviors in the shape, and how that folds in with a very large amplitude light curve is kind of a mystery. So there's one final thing that I want to tell you about that I've also got. I have a project called RECON, which is actually NSF funded. It is, I've got 50 plus telescopes in the western United States. They're all at fixed locations. It's a fixed pattern, and you let the shadows come to you. And this was designed to work in the pre-Gaia era, but it is still an efficient strategy for getting that first anchor point, first occultation. But the point here is this was designed for 100 kilometers or larger. And we're finding that in the cost for this whole project, which is in its fifth year right now, was about $1 million. And this is kind of the top end range of what you can manage to get out of a traditional RNA program. Okay, so the opportunity here before us is that we've got a tool that lets us go and sample populations of objects. You can pick an object of interest, you can pick an unbiased sample, whatever you want to get, we can go out and chase these things, know about them. And that's pretty much anything that we know. Any population, any distance, up, say 5 kilometers and bigger. It provides much better context for mission results. We can probe many more objects than we can do with missions themselves with far less cost, even though it's more expensive than a traditional RNA program. For instance, would you like to get measurements of 10 cold clusters to see how many of them are contact binaries or whatever their shapes are. And I think this reaches down almost to the level where they start getting into the serendipitous occultation surveys. Okay, so the sound, I've said it before, occultations, you don't chase these for food. They're not easy things to do. It takes a lot of work, a lot of coordination. I've developed this network of people and equipment and how to run these large organizations. But I cannot see how to sell this in a traditional RNA program. I go to solar system observations, maybe I'll get one event, and that's just too slow to get a population study. We need to find a way to leverage the mission investments we're doing and bridge this gap. I think that it is sort of like the equivalent of the TRL gap. If you're familiar with instrument development, we've always had this problem going from TRL, from the brainstorming ideas down in the TRL 0 to 3, and then from 4 to 6. There's a lot. It's harder to get funding for something that's pretty well ready to go, but not quite ready to be spacecraft. And that featured very strongly in the last decadal surveys. How do we fix this TRL valley of death? I think we've got the same thing going on here in terms of science and exploration using this occultation technique. It's smaller than a mission, but it's bigger than a regular RNA program. And we need to figure out how to close that gap, how to fix this problem. So I recommend that we reach out to NASA and say, hey, investigate this. Find out a way that we can fix this problem, how we can bring focused resources to bear for doing these kinds of occultation surveys. And kind of what I'm hoping that if you guys agree, within that, the small bodies community and the SBAG itself, is that we can ask them to look into it. And just as a reminder, this is a near-term problem. If you push this off to the decadal survey, you're going to leave a lot of science on the table. We need to move a little faster than that. Faster the better. But with that, I will take questions if there's time. Thanks.
Thanks. Do we have time for that one question? Meg. Yeah, I'll repeat it. The question is whether having LSST, which will have another 10 years, though not quite as good as Gaia, whether that will help.
Well, okay, so you're getting into, there's a very, very long answer. But basically, you won't be able to get the smallest size ranges based on the LSST data, because as you start getting enough arc length on the smaller objects, you're working with a degraded catalog, and it's going to reduce you're going to increase the uncertainty in the ground tracks for those occultations. So it helps, but it's not going to solve the problem.
Mike. Question from online. If the equipment is only 10%, what is the big cost driver?
The cost driver is travel, logistics. I put 2 scientists per telescope. You have to get them there. If I can only send one of my trained experts, that cuts the cost a little bit. I'm trying to keep the cost down, but you got to ship this equipment across the world and get it there and get it back. It's all the stuff it takes to actually do it, not the cost of the equipment. And you know, maybe if I get better and better at this, I could see trimming the cost by a factor of 2, but it's hard to get below even that, and that's not always possible even then.
Thanks, Mark. I think we're going to have to move on. We're going to do one more talk before lunch, and then we are going to come